Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm here with Minal Sawant of Xilinx, who's going to talk today about radiation hardening of chips. Minal, when we think about radiation hardening, this typically goes into mil-aero and deep space. I mean, when you think about chips that get launched into outer space, those all have to be radiation hardened, right?
So yes, you're absolutely right. When you're talking about space applications, the requirements are quite different, right? There is levels of requirements that electronics have to be able to perform. There's two types of radiation types, tolerant devices or radiation hardened type of devices. So it depending on which portion of the Earth's orbit that the spacecraft may be launched or a scientific mission may be launched, the requirements can be very different. So think about it as you go away from the Earth's surface, the requirements get more stringent, and that's where it becomes more important to have radiation hardened electronics versus radiation tolerant electronics.
Just a function of there's more atmosphere closer to Earth that can disrupt the particles.
Yes, it typically our Earth's atmosphere absorbs the particles, right? So we see a very small percentage of the particles travel through the Earth's atmosphere. Sun being the biggest source of radiation, the particles that come from the sun, as you're further away from the Earth's surface, obviously you have more bombardment of cosmic rays. So that's why as you get closer to the Earth's surface, there's less and less amount of radiation. The Earth's atmosphere filters out a lot of the radiation, and you have only some particles that come through, and those are known as the neutrons or alpha particles.
Let's dig into this.
Sure.
Minal, what are we looking at here?
If you look at how the terrestrial and space environment is divided, right? I like to show this because what it shows you is the difference in the various types of radiation particles that the electronics have to bear, as I mentioned to you earlier, through the sun as our basic source. So if you look from bottom to top, right, if you look at sea level or our systems here at ground level, the amount of rays is really very negligible. Not zero, but very negligible. But as you go further away from the Earth's surface towards what we call the Qumran line, which divides the space and the Earth's atmosphere, the different types of particles start becoming more dominant. So within the Earth's atmosphere, you're going to see something called the neutron flux, right? You have to think about them, for example, military aircrafts or avionics systems, right? Those are the ones that are going to have mitigation to be able to withstand the neutron flux. As you travel a little bit above the Qumran line and beyond, you divide the orbits into a couple of orbits, right? You have the low Earth orbit, you have the mid-Earth orbit, and then you have the geosynchronous Earth orbit. And beyond that is what we call deep space. As you look on the right-hand side, right, as you go up the line in my chart, as you see, the LEO orbit is really up to, between 500 kilometers to 1,500 kilometers above the Earth's surface. And that's where you're going to see a lot of these satellites like the broadband internet satellites, right? We hear a lot about SpaceX, and that's the broadband internet satellite constellations where they sit. And that's really dominated by the particle called protons. So protons and some amount of what we call heavy ions. So different types of particles, and they interact with the circuitry from a semiconductor perspective. Think about it as a 0 and 1, right? You can flip the a CMOS circuit, or you cannot flip from a 0 to 1 or 1 to 0. This is what the particles can do depending on the energy that they come through. They can have secondary emissions, which can cause a functional change, or it can be absorbed into what we call total dose. So two different types of things can happen with radiation. And then as you go higher up the orbit, for example, in the geosynchronous Earth orbit, which is 36,000 kilometers and above, this is where mostly it's dominated by what we call heavy ions. And they have a different characteristic in how it interacts with the silicon portion of a CMOS circuit, for example.
So, what makes one level different from another? What do you have to think about at each new level?
So at each new level, you have to think about what is the amount of radiation that's going to get absorbed, and how is it going to flip the circuit, or is it going to affect the functionality of the circuit? That's number one. You could have a functional failure, meaning you could, where it was expecting a one, you could have a zero. Now, it depends on what kind of application it is. If you're really collecting just images, if I lose a bit of pixel, it's not that critical, right? When you're imaging and you lose a bit of pixel, I can scrub it and I can recapture that image. But if it's a functional failure where it's a very critical portion of the spacecraft, for example, if it's in terms of, it's a navigation satellite or it's a reconnaissance type of a satellite where each bit is very critical, where it has to be 100% on at any given time, you cannot afford to have a bit flip, right? So those are the characteristics you would look at when each of these layers that will have to decide what kind of product or what kind of circuits and mitigations you need to apply.
This is a lot more complicated because it goes into things like ionization that you don't really have to worry about when you're sitting in a terrestrial application, right?
That's correct. If you think about it, the basics of a single event obsec, it really depends on what kind of particle you may have incident upon your circuit. So there's two ways to look at it. It can have a direct ionization, which means the alpha and the beta particles, which are low energy protons, can cause a bit flip. There's a second type of challenge that you also have to look for is indirect ionization. And this is mainly driven by particles like the neutrons and protons. So direct or indirect, so depending on the type of particle, you could have different type of effects on the circuitry, and that's what you have to mitigate for in these applications.
What does this do to the cost? If you're thinking about developing a chip that's going to run in one of the inner layers of the atmosphere versus deep outer space, what has to go into the chip that is different in deep outer space from what you're dealing with over the Kármán line?
Typically, what you would look for is how much can the device withstand, right? So what do you have to do differently? And there are various ways that you could mitigate for it is, for example, you can harden the device through radiation hardened techniques. It's called radiation hardened product, which is done through process. It can be done through design. You triple module or you harden the circuitry compared to what we call our commercial grade products, right? Which is less hardened in comparison. And the third portion is software mitigation as well. So there are various layers of mitigation that you can apply. As you go further up the orbit, you have to have more and more hardening techniques because there's more radiation. So the circuit or the device has to be able to withstand that. So that's one. The second thing also you have to take into consideration is packaging of the product. So that's also something you have to mitigate for because our plastic or organic packages cannot withstand the temperature variations in space, or they cannot withstand, for example, even during launch, you have the G-force, right? And so to be able to withstand that G-force, our organic packages can do that today, or plastic packages. You have to think about, very robust materials like a ceramic package, which has much more robustness as you go through the different layers. It's not just radiation hardening through process and design and software, it's mechanicals as well, which is packaging, and then it's electricals as well. So you have to be able to test the product and guarantee its reliability over a long period of time. For example, GEO, right, could be missions that are, 10 or 15 years in lifetime, versus a LEO could be 4 to 5 years in lifetime. So there are differences in the types of orbits, what the requirements are.
Are there learnings from this that you can apply into other markets, such as safety critical things like automotive, even industrial?
I think it's both ways. I think you could learn from the automotive market, and I think there is learnings from our market in space as well to be applied to automotive as well, right? For example, security or even functional safety kind of requirements or yield improvements, right? We have failure in time requirements for automotive, which is 0 parts per million, 0 ppm. Similarly, for space, you have to have extremely high reliability and very, very low fit rates because you really don't have an option, right? Failure is really not an option in space.
One of the interesting things that's going on in space these days is we're starting to get into the application of AI and machine learning. So some of these things may be unmanned vehicles, and they have to be able to adapt and function just as well as if somebody was controlling them and can take over. What sort of impact does that have in terms of the design here?
So if you think about, as you mentioned, machine learning in every facet of our life is starting to take dominance, right? Same applies to the space applications as well. Though we are at a very nascent stage, we are going to see a lot of these use cases being applied to machine learning. Let me give you a good example. I love this example because I was very surprised when I learned this. 66% of our Earth is covered in clouds at any given time. So if you think about all these satellites, say, think about an imaging satellite that is, has these big hyperspectral imaging cameras. It's taking pictures of the Earth at any given time, right? Now, with the Earth being covered in clouds 66% of the time, the images are really just of clouds that you're taking. But what happens on onboard processing is you take the images of the cloud, you have to, you sense the images, you have to pre-process it, you have to compress it, you have to store it, and then you have to send it back to ground for post-processing, right? And for satellites, we know the bandwidth is extremely limited. You don't have a lot of bandwidth. And then the data comes from the ground station, it gets processed, and decisions can be made. Think about a use case where if you had machine learning algorithm on board that could detect a cloud. So if you had a cloud detection algorithm, it takes the image instantaneously, is able to say, hey, it's an image of a cloud. I don't need this because it doesn't give me any data. Let me discard it. You've saved everything in the signal change, right? You don't have to pre-process, you don't have to compress, you don't have to save the image, you don't have to use very important bandwidth. So those are the kind of use cases that we're going to see quite a bit. And there are so many, right? Predictive maintenance, making intelligent decisions, changing algorithms on the fly, depending on what data is being sensed. From a machine learning AI use cases, image detection or image classification, I think we're going to start seeing a lot of use cases.
We're also starting to see an increase in density as we start getting into some of these applications. So you think about the chips that went into outer space in the past, they were pretty much older processes that they were developed at. As we get into new processes, everything's a lot denser. Now we're not just worried about flipping a bit, we're also worried about potentially wiping out some transistors, right?
Yes, it's not wiping transistors, but I would say, you're talking now of multiple bit errors as well. So it's not a single bit anymore. You could have multiple bits because you're packing such millions and millions of transistors in such a small space, right? Or a small size. So absolutely, as you think about these advanced technology nodes, you do have challenges with multi-bit upsets as well. But the way, at least at Xilinx, we look at it very differently from an architecture perspective. On a design side, when we are actually architecting the product, we have mitigations in place in very critical portions of the device so that we are able to mitigate for it even on our larger density device. In our case, we just announced a Versal product, and for space, based on our initial radiation data, it does show it a very good applicability for space, even with millions of transistors in a small size.
Any impact in terms of power and performance when you're designing these and even area? Is it larger because you now have to harden these for radiation, or is it pretty much the same?
No, you do. There's always a trade-off, right? There's a trade-off with power and performance. They just go hand in hand every time. And for our space applications, there's an additional layer of what we call the swap, right? The size, weight, and power. So we have to always care about all those three attributes. Anytime you condense the size of a system, it all adds up because everything launch cost is all dependent on the weight of the satellite, right? So the more you can reduce the weight of a satellite with either having a smaller solution, an integrated solution, less mitigation, or more advanced technology nodes, it always helps with the size, weight, and power. But when you come to power and performance, there's always a trade-off. So there can be solutions, depending on what it's in the functionality on, especially on the payload side that we typically, a lot of processing is done. So you have to make that choice of, you're getting so much sensor data. I need a lot of processing, right? So I do need a very advanced capable part versus if you're on the bus side, for example, where it is more about control and it's more about functions which are very similar in every spacecraft. Power can be saved over there in a different way. But yeah, there's always this tussle. I want more performance, but I don't want more power because in space, there's no heat dissipation, right? Where are you going to send the heat to? So Thermal challenges are very, very key. And as we get to these kind of dense devices, we have to look at what are the new ways of solving this problem.
What's the projected lifespan of these chips?
For us here at Xilinx, we definitely have a very long extended life cycle for these products. 15 years and above is sometimes a lot of missions can go, and we do supply beyond whatever our requirements are, but definitely for 10 to 15 years of mission life is what we design the radiation hardened and the radiation tolerant product lines.
And some of them last much longer. We're seeing in photos from Mars of technology that was developed, what, in the 1990s or early 2000s?
Yes. Yeah, and it's still working. That's the amazing part, right? Opportunity is still running on the surface of Mars, and it was supposed to be working only for months, and it's been years since it's working. And we recently had Perseverance launched and landed on Mars as well. If you've noticed, as you rightly pointed out, it started as a small toy car with the first version of the Mars rovers. And today's Percy is the size of a Ford 150 truck. So you can imagine how much of electronics has been added. And with that comes the capability and more data that can be collected. So much has evolved, but the science that goes behind it to ensure, we collect that data so we can send humans to Mars one day is right now, that's the experiment with Percy.
And this is all moving at the rate that we're seeing in other markets too, right? So you think about a car back in 1990, it was almost no electronics other than your windows and radio. Now it's entirely electrified. We're starting to see the same thing out of these devices that are going into space too, right?
Right, absolutely. That's why I said for me, the biggest example is the rover, right? It was a little toy car. I've seen it at JPL. And the last version I was able to see was like a Ford 150 truck. And it has so much capability, and that's what we need, right? These are science experiments. We want to know how to go to moon and beyond. So the landscape has definitely changed in terms of electronics.
Are they configurable like a standard FPGA? So if something doesn't work within a system, can you now configure part of the logic to work and say, okay, we can make up for that at least partially?
Right. So that is the other change that we're seeing in our market space, right? You talked about systems, say 10 years ago, right? It was a very fixed function type of a satellite, for example. And then you had to launch another one in the next 10 years because now you needed to change something, or the algorithms have changed, or the FAA requirements have changed. But the trend now is like the other markets, faster time to mission and faster time to deployment, which means our users are designing more with multifunction platforms. So you have a base, and now you want the capability to be flexible so you can change the functionality on the go, right? So you're absolutely right. Reprogrammability is very, very key. And one of the examples I was talking about, is if you want to change the algorithm, now you don't have to send a new satellite up there. You can actually just send a new bit stream. For example, in our case of an FPGA, you can upload a new bit stream and configure the FPGA now to perform a different portion of the algorithm or change the algorithm on the fly. So we're starting to see that in the last several 5 years, systems are being purposely designed. It used to be, oh, it's nice to have as a feature, but now it's like must-have requirement on satellite design that I want the capability of it being a flexible and reprogrammable satellite systems.
Do you foresee massive changes coming the same way we are in other markets? Will this continue to roll out and we get denser and denser chips and more technology and potentially chips in a package?
Oh, I hope it's going to be chips in a package because I think we're going through a resurgence in the space applications right now. If you notice all the news bites coming out, right? Everybody wants to send a constellation out there, every country, right? We have our own SpaceX, we have Amazon Kuiper. Europe is sending something called Telesat, or Canadian satellite constellation. South Korea is sending their own constellation. Every country is looking to send a constellation. And the whole idea being because launch costs are getting cheaper. And that's because of not just advanced electronics. Of course, we do have advanced electronics or advanced node technologies and capabilities. Typically, space has lagged behind commercial by 4 to 5 years because it's typically been a risk averse market. But that's changing now. Everyone wants to have the capability, also because of the rising threats in the geopolitical nature that we see around the world, right? Every country wants to have that capability. So definitely, I think this whole Space 2.0 or new space terminology that we hear in the next 4 to 5 years, we're going to see a huge proliferation of that. And even our traditional customers or traditional users, right, and government is also wanting to create those flexible systems and not lag behind in technology adoption. It's a great time to be in space actually right now.
And also, when you think about what happened in a cell phone, where it went from this big brick to now a small phone that fits in your pocket with lots of functionality, the same thing can happen in a satellite too, right? I mean, we can have satellites that are much smaller. You don't have to launch these big satellites that you did in the
Mhm.
past.
Absolutely. That's the reason you're seeing so much of activity in our space, right? You can have satellites from like what they call the nanocubes to small sats to, then the sizes go up, right? Then you have your, less than 50 kilogram, then you have your less than 100 kilogram, and then you have the big birds, which are 500 to 1,000 kilogram type of satellite. So you see that whole chain and so much image or information that we can gather now, and that capability to utilize that information right away, right? Whether it's for fire detection in Amazon or in California, right? And making a decision right away. I think that's where we're going to see a lot of proliferation, whether it's from a SAR imaging or from a hyperspectral imaging perspective. Use cases are going to explode in terms of what we can do with space applications.
Minal Sawant, thanks for a great explanation.
Thank you, Ed.